How does ADC conversion time affect signal accuracy? Imagine trying to catch a moving ball with a camera that takes a few seconds to process each shot. The longer it takes, the more the ball might have moved, right? That's similar to what happens in analog to digital conversion. When an analog signal is turned into digital data, the time it takes to do this process can really influence how true the digital version is to the original. Conversion time is the total period the analog to digital converter needs to sample the input signal and then turn that into a digital number. This includes the sampling time, when the converter's sample and hold circuit captures the voltage, and the actual conversion time, when it processes that voltage into a digital code. If this process takes too long, it can cause problems. One key factor is the sampling time. The converter needs enough time to accurately capture the voltage. If it samples too quickly, the sample and hold circuit might not fully charge to the input voltage, leading to errors. Think of it like trying to take a picture too fast. The image might be blurry or incomplete. Longer sampling times give the circuit more time to settle, resulting in a more precise reading. Next, higher resolution converters, like those with 12 bits or more, requiring more internal steps to resolve the voltage. This means they take longer to finish each conversion. If the conversion time is too short, the process might not complete all steps properly, leading to inaccurate digital output. It's like trying to solve a complex puzzle in a rush. You might miss some pieces. Conversion time also limits how fast the ADC can sample signals. According to the Nyquist theorem, to accurately reconstruct a signal, you need to sample at least twice the highest frequency in the signal. If the conversion takes too long, the sampling rate drops and you risk aliasing, where high-frequency signals appear as lower frequencies, causing distortion. This can make the digital data less reliable, especially for fast-changing signals. Another aspect is the stability of the input signal during conversion. If the signal changes while the ADC is converting, the digital output might reflect a mix of different voltages. This distortion is more likely if the conversion takes longer and the signal is rapidly changing. For example, in fast sensors measuring quick movements, longer conversion times can cause inaccuracies. Sometimes, longer conversion times are used intentionally. Techniques like oversampling and averaging multiple readings can reduce noise and improve the effective resolution. But this only works if the input remains steady during the entire process. If the signal fluctuates, averaging might introduce errors instead of reducing them. Power consumption is another consideration. Slower conversion times often mean lower power use because the ADC isn't working as hard. This is helpful in battery-powered devices where conserving energy is important. But it's a balancing act. Slower conversions mean less power but potentially less accurate or timely data. In real-world systems, engineers carefully choose the conversion time based on what the application needs. For example, in a temperature sensor, a longer conversion time might be acceptable since the temperature doesn't change rapidly. But in a high-speed data acquisition system, quick conversions are essential to keep up with fast signals. To sum up, ADC conversion time impacts how accurately the digital output reflects the original analog signal. Too short, and you risk incomplete or inaccurate data. Too long, and you might miss important changes or reduce system responsiveness. Finding the right balance ensures your system captures signals faithfully without sacrificing speed or power efficiency.